can we can draw p-n junction diode. P-type semiconductor is placed in contact with n-type semiconductor, and in this case p-type semiconductor is connected to negative terminal of the battery, and EMF of the battery will be much stronger than that of the battery in forward bias. In this case V is the EMF of the external battery, in p-type there are holes as majority charge carriers. Circled positive sign means these are holes. Holes are majority charge carriers, conduction electrons are minority charge carriers, and on the other side in inversion, conduction electrons are majority charge carriers, holes are minority charge carriers. Now we can denote negative terminal of the external battery. This is the negative terminal and these are positive terminals, and this is a strong battery in comparison to that of in forward biased in junction diode. Now we can denote the direction along which p-type holes will be moving. In what direction holes will be moving? Holes will be attracted by the negative terminal, so these holes will be moving away from the junction, because this negative terminal will attract these holes in this direction. Negative terminal of the external battery will attract the holes. So that's why holes will be moving away with respect to the junction. What will be the direction of motion of the conduction electrons? Conduction electrons will be repelled by the negative terminal of the battery, and this conduction electrons will be traveling towards right. Similarly, we can denote the direction along which conduction electrons will be traveling. Conduction electrons will be attracted by the positive plate of the external battery. Holes will be moving towards the junction. In this case, we can denote the depletion layer. Width of the depletion layer increases, that means depletion layer becomes thick during reverse biasing. Now we can denote the different immobile ions in p region in depletion layer actually. So here we should have negative ions, and in depletion layer in n region we should have positive ions. Now we can denote fictitious battery. What is the function of EMF of this fictitious battery? It opposes further diffusion of majority charge carriers up to knee voltage, and this region is called depletion layer. And its thickness increases, its width increases, and this is depletion layer. And its width increases, or it becomes thick during reverse biasing. Now we can denote the direction of reverse current. It will flow from N region to P region, because holes are migrating from N region to P region. Holes are migrating from N region to P region. So this is what reverse current. This is called reverse current. In this case, reverse current I is the reverse current which flows from positive terminal to negative terminal of the battery. So this is the direction of reverse current. Under bracket of I, what we can write? Reverse current under bracket of I, what we can write? I is the reverse current. I is the reverse current which flows from N region to P region, and which is produced due to a migration of minority charge carriers. Migration of minority charge carrier. Minority charge carriers from one region to another region of PN junction diode. Migration of minority charge carriers from one region to another region. One region to another region of the diode. Another region means from P region to N region, or N region to P region of the PN junction diode. PN junction diode. PN junction diode. In this case, this negative plate or negative electrode of the external battery, this is the external battery. This is the external battery, and this negative terminal repels this conduction electrons towards the junction, and this conduction electron will cross the junction, and this reverse current will flow in the opposite direction of motion of this conduction electron. So in this way, reverse current is produced. Similarly, hole in N region is repelled by the positive electrode of the external battery, and this hole will be repelled towards the junction, and this hole crosses the junction. That's why reverse current flows from N region to P region. N region to P region. What we can say, this is reverse biased PN junction diode. Reverse biased PN junction diode. And in this case, we can draw a reverse characteristics. Along this horizontal axis, obviously voltage V is plotted. And what is V? V is the EMF. V is the EMF of the external battery. EMF of the external battery, which is plotted along the horizontal axis, and along vertical axis, along negative y axis or vertical axis, reverse current I is plotted. Reverse current I is plotted. I is the reverse current. I is the reverse current which is plotted along vertical direction. Along vertical direction. Vertical direction. Now we can plot, and this point is the origin O, and now we can plot reverse characteristics. From O to A, this point is, say, this point is G, not G, say this point is C. This point is C. Up to this point, current increases negatively exponentially. Then beyond this point, current will increase negatively abruptly, almost parallel to the current axis, almost parallel to the current axis. And this is reverse characteristics. And here this is what this region is D. This region is D. Here from this point we can draw normal. At this point, voltage V is equal to minus Vz. Voltage V is equal to minus Vz. And this is reverse characteristics. I versus V graph in for reverse biased is called reverse characteristics. This is known as reverse characteristics. Reverse characteristics. From the point O, from this point O to C, obviously current increases or changes exponentially, and here this current is reverse current. Obviously here what we can write, reverse current increases exponentially. Reverse current increases negatively, obviously, increases exponentially. With this reverse biased voltage. Reverse biased voltage V, as according to the equation, as according to the equation or to the mathematical relation, as according to the relation I is equal to I0 e to the power EV by 2 kT minus 1. And beyond this region, obviously beyond this region means if we consider this region from the point C to D. So in this region, reverse current in this region, obviously reverse current it should be exponentially. Reverse current increases very slowly and exponentially. Here what we can mention, very slowly and exponentially. Here it should be corrected very slowly and exponentially. But in this region from C to D, from this point C to D, what we can write, reverse current increases. Reverse current increases abruptly. Reverse current increases abruptly. Comma, abruptly with the voltage, comma, almost parallel to which axis? Almost parallel to the current axis, almost parallel to the current axis. And in this case, this voltage V equal to V is equal to minus Vz. Voltage is the Zener voltage, beyond which voltage reverse current increases abruptly with the voltage and almost parallel to the current axis. And this voltage V equal to Vz is called Zener voltage. It is called Zener voltage or avalanche breakdown voltage, or avalanche breakdown voltage. Avalanche breakdown voltage. Avalanche breakdown voltage. That means if we draw the reverse characteristics again, this is the reverse biased voltage and this is the current axis. Current axis, reverse bias voltage. Initially current increases very slowly following exponential relation, then increases abruptly, and this voltage is equal to minus Vz or negative voltage, and this voltage is called Zener voltage or avalanche breakdown voltage. Zener voltage. Beyond this voltage current increases abruptly, and from this point is C. Obviously if reverse bias voltage is greater than equal Vz, in that case the reverse current increases abruptly. Increases abruptly means conductivity of the semiconductor increases by very large amount abruptly. That is its conductivity. Its conductivity increases and becomes very large, and becomes very large. Reverse current increases abruptly, that is, it in conductivity becomes very large in this region, and we can denote the region as CD. So in this region, that is, the region is CD, comma, the reverse biased PN junction diode, reverse biased PN junction diode is known as Zener diode. In the region OC, of reverse characteristics, the expression of reverse current is I equal to I0. I is equal to I0 bracket e to the power minus EV divided by 2 kT minus 1 divided by 2 kT minus 1. This is the expression of reverse current of PN junction diode. Expression of reverse current. The expression of reverse current in the region OC, in which the diode offers high resistance against the current, reverse current, in the region OC. In the region OC, in which the reverse biased diode, reverse biased PN junction diode offers high resistance and its conductivity is very low, high resistance against the reverse current, against it. And what about K? K is Boltzmann constant. K is Boltzmann constant. And capital T, what about capital T? Absolute temperature of the PN junction diode. Absolute temperature of the PN junction diode.